Since this project had so many moving parts, I figured I'd do a little walkthrough just to see what it looks like and give myself a little context if I ever want to revisit it. So this is the block diagram that I used to put together the main pieces for running the TIS100 node on real hardware. The way that Vivado allows you to connect these complex digital blocks is this block design interface here. Basically, each of these blocks represents a component in the FPGA that allows for sort of parallel compilation and gives a standard interface to give you interchangeable parts that can be configured independently. The main thing to see here is the processing system. So this is the ARM processor that's integrated into this FPGA. Once this opens up, you'll be able to sort of see the customization. At a high level, you have the processor cores itself, and then all these different peripherals that can be configured to either connect to the FPGA or to go out through dedicated pins. In this case, I'm mostly just relying on the serial connection that allows me to get a terminal onto it, and the AXI master interface over here, which is how it communicates with my TIS node in the FPGA logic. So the code that I wrote is encapsulated in this TIS100 node. Basically, this is just a wrapper that will take the input from the processor, which is basically just register reads and writes, and we'll translate that into the commands that the node needs. So loading the instructions onto it, writing data in, and reading data out, and seeing what the current status of the processing is. So all of the Verilog code that I wrote is contained inside this node. So going back up to see the hierarchy, you can see that inside the top level design, you have these different nodes, and in the TIS100 node, you have the AXI wrapper, and then finally inside the actual instance of the Verilog, which has the modules that perform the computation logic and state management. So once this gets combined, I'm able to then view a schematic that is a representation of this logic in the actual hardware. So here I can see that if I look at the actual device under test, you can see the way that it tried to collapse a lot of the inputs and outputs into some a little bit less sensible names than they are in the actual code, and how it then has all of the interconnection between the different sub-pieces of the node. If I go in deep enough, I can actually see the flip-flops and lookup tables that make up that are actually implemented in the hardware. So this is what actually will be reserved on the FPGA in order to do the processing. So this has already been compiled, so I can then see the synthesized design and then the implemented design, which actually puts this logic onto the hardware. So if I take a look at the schematic from the implementation perspective, or the utilization, I actually have that up down here. I get to see the how much of each of the resources, the lookup tables, the slices. They're not using any memory or DSP apparently, but with this node using well less than 1% of the total resources. And for a lot of these, if I drill down into the overall utilization, I can see that over half of that, or about half of that, is actually being used by the wrapper, the node is only using a fairly small amount of some of this resource utilization, and of that, the RAM is using a lot of the probably is the biggest piece. The ALU, which is just doing a very small amount of arithmetic, is made up of very few pieces of logic. But going to the device itself, I can see how this actually maps onto the actual physical components of the FPGA. Over here, I have the processor itself, the PS7. This is the same PS7 that was in the original block diagram, which contains the ARM and some of its peripherals. And the blue here is the nodes that actually make up the design that I have. They break down into the individual registers here, and let's see, more registers and lookup tables to just get a little idea of how these all connect. You can see the nets that go between all these different components. So in this particular case, this is well, hard to make out exactly what component this is, but something in one of the wrapper components apparently. So to actually get this all built, I ran generate bitstream. So this goes through using the Verilog source code and that block diagram, and then maps that logic onto this chip, and then generates a bit stream that's used to configure the FPGA in the actual hardware. So once I've done that, I went to export the hardware. So the way that Xilinx tries to make building software for FPGAs a little easier is that you're able to generate a version of a description of this design that can be loaded into C code running on the ARM processor. So I've already exported that, and then I have to launch this Vitis tool. So this is basically just a fancy version of Eclipse. That has a bunch of the special logic that Xilinx has set up in order to be able to communicate with these peripherals and have the right tool chains for compiling everything. While I wait for that to load up, I can also start up a serial terminal that'll be able to see the input and output of the processor and FPGA logic as it's running. Just set it to the right port. So this will allow me to see the output from my process. So the way I'm going to be interacting with the real hardware is I have a JTAG connection that will write the process that I'm compiling here into the RAM of the processor, and I can actually put in breakpoints and do debugging as well. And it's also able to load the FPGA design. So here's the source code that I'm running. Now you can see that I have a particular TIS100 program compiled here. It's 8 instructions, and it implements a simple multiply. This is just the output of my compiler when I loaded the example test multiply program that's in the project, and set it to output a C array. Just creates this object that I can then put into the source code. So what this program is going to do is it does some configuration of the GPIO connected to the processor. This basically just lets me have an LED and push button that I can use to trigger the actual run. And then it loads the instructions that we were looking at over here across that AXI interface into the memory on the FPGA, and then it will write a 5. So right now, this is the value we're going to be multiplying by. So it's 8 plus 2, so 10. So we're going to do 5 times 10, and then 100 times 10, which is going to saturate, which should be 999. So I will go to run this. So this is basically just telling the debugger to load the FPGA and program logic onto the processor. All right, waiting for me to press the button, and there you go. You can see that it wrote 50, got, wrote 5, got 50 back, wrote 100, got 999 back. Now, if I were to change the amount we're multiplying by, say change it from 10 to 14, rebuild the project. So this will just make it so that when this first loads the instructions, it'll just send one of the constant values in one of the instructions to a different value. And I will clear this. So this is also actually building an SD card image, so I can boot this from an SD card as well without needing to use the JTAG. So I'll just go ahead and run this. Go over to the processor, the serial terminal. Okay, ready for the button. And here I can see that instead of 5 times 10, I'm getting 5 times 14. So that checks out. And unfortunately, the 100 times 14 is actually also still saturating at 999, but that's still working as expected. So the mapping of that AXI interface basically just means that to read and write from the hardware, I'm writing registers at some offset in memory and reading the results back. So to tell if the operation is completed, for instance, I read a register that has whether it's ready for the next write or read, and then just masks off the state that I'm looking for. So yeah, that's getting this all put together and up and running on real hardware.